All right, folks, we're moving on from, we looked at gases, and now we're going to move into really the core of the chapter, which is solids and liquids, much more interesting to chemists. We have said, when we looked at this animation, and go back and play with that, it's fun. If you go back and play with that animation, we said gases, the particles were independent. There's no stickiness, there's no attractive force between the gas particles, whereas the liquids and solids, so say liquid and solid particles stick together. There's some force that's making those stick together, and that force doesn't exist for the gases. So at the bottom of this page, 8.10, I have some examples. And here's kind of funny. We said there's gases. And here there's Cl2. And Br2 is similar. And I2 is similar, yet Cl2 is a gas. Br2 is a liquid. And iodine is a solid. Similarly, this C4 hydrocarbon is a gas. That's butane. There's C5 is a liquid, C20 is a solid. And similarly, SO2, PbO2, this molecule, they're very similar, yet gas and liquids and solids. And so it comes back to almost the joke I made on the first day of the semester, where I said, well, these are not sticking together. Why are these sticking together? Why do liquids and solids somehow stick together? Well, somewhere there's something that looks like that, and there's something that looks like that. There are somehow opposite signs, and I'll draw this little like dashed line to show that's an attractive force between those things. Those are somehow sticking together. So what we're going to do is sort out all the ways that particles can get this plus minus business and stick together. And then we're going to talk about, okay, how do those work? What do we call them? And what's the relative strength of those things? So if we go to page 8.11, we're coming back to something we already know, which is always the best place to start. If I look at these, I say, oh, you know what? Those are ionic compounds. That we saw in chapter 3. So, oh yeah, I remember that. And then if I think about, well, wait, what are these really made up of? Well, they're ions. They're ions. And we had established this way back chapter 2, chapter 3. So there's some kind of attractive force. So if I think about, oh, why would they stick together? Well, oh, I've given it away. Well, they're all ions. And what's making them stick together is this. The plus minus. Well, we didn't give it a name. We just said it was electrostatic attraction or something like that. But we might as well give it a name. We'll say, well, this is sort of an ion force. Well, it's the plus minus, well, maybe we can just say plus minus ion attractive force. That's the sort of intermolecular force, we're going to use that term, or the sort of glue holding them together. Well, these can also be solids, HCl, H2S, SO3. Now, if I think these are all molecular compounds, there's no metal there. So what category of molecules are these? Well, if I start drawing them and thinking about things like that, oh, I could go. Well, these are, we're going back to chapter 4. Reminder, chapter 4. These are polar molecules. And this can get complicated, but for our purposes, we usually just say, well, remember, it's asymmetrical. Everything on the central atom is different. The big idea is somewhere on a polar molecule, I get a delta plus and a delta minus. Somewhere. So that's polar. You might want to go back and review chapter 4, like, oh yeah, well, how did we decide if it was polar? Well, how do these things stick together? Let's take this simple one, HCl. I know chlorine's very electronegative. It's fluorine's neighbor. So I know that, oh, that's going to be delta minus. The electronegativity for chlorine's like 3, hydrogen's 2, 2.1, something like that. So if that's minus, that's plus. Well, if I put another molecule next to it, there's my other HCl. It's also plus and minus, which means, oh, I've got Professor Paula Abdul said that. So polar molecule, polar molecule. Now, sometimes we use the word, if something has a plus charge and a minus charge at one end and the other end, we say it's a dipole. Polar molecule, the generic term is dipole. So we call this dipole, dipole. Dipole, dipole. That's what we call this force, this glue that's holding these particles together. And by the way, we're going to use this term again and again and again. Intermolecular force, intermolecular force. For our purposes, it means the glue. What's the attractive force that's keeping these together? So this will get abbreviated again and again and again as IMF. Okay. So there's our first one. And we remember this. Oh yeah, if I think about this, this is pretty easy to understand. And oh, this is a little trickier. I have to find the polar molecule. But oh yeah, there's a plus-ish and a minus-ish. And Professor Paula Abdul says they'll stick together. Well, there's a special case of dipole-dipole. This is page 8.12. These are all polar molecules as well. They're all polar molecules. But they have something in common that might not jump out at you right away. But if I started to draw Lewis structures of these, H, O, H, there's water, H, N, N, there's ammonia, NH3, CH3, H, C, H, H, O, H. I get to this, H, N. What they all have in common is their polarity involves that. They're all polar molecules that have an OH or an NH. There's also this one that's not as common, but we'll come back to that. So they're polar, but they're very, very strongly polar. Oxygen's very electronegative. Nitrogen, fluorine are very electronegative. So this bond gets really super plus, plus, minus, minus, minus. The polarity of that bond gets quite polar. The charges get pretty strong, and so the entire molecule is very polar. And we can draw a nice little picture here. What about a bunch of water molecules? And now we know that the angle is not 90 degrees or 180 degrees, 110-ish or something like that. So the water molecules are bent. If I line up another one here, and I remember, okay, oxygen's very electronegative. Hydrogen, not so much. So, oh, bingo. There's my intermolecular force. Now, sadly, we have a terrible name for this. I apologize. I just work here. But we call this hydrogen, partially positive hydrogen, sticking to a very electronegative atom, oxygen, nitrogen, or fluorine. We call this hydrogen bonding. Hydrogen bonding. HB. It's not really a bond. It's a way they stick together. It's roughly the strength of about 10% of a regular covalent bond if we think about bond dissociation energies. It's not a bond. It's a kind of stickiness. It's a kind of IMF. Okay. That one, same thing, isn't a big stretch for us. We're like, oh yeah, we knew about electronegativity. We knew about polar molecules. We knew, okay, oxygen, nitrogen, fluorine are very electronegative. So, okay, there's a special case of dipole-dipole that's very strong. It gets its own name. Now it's going to get a little bit trickier when we go to page 8.13. Well, you know what? Let me go back to that page. I want to make a couple more examples. If I think about, just so you don't think that it's only oxygen, nitrogen, only oxygen, hydrogen. I could have hydrogen, nitrogen, hydrogen, nitrogen, and the same thing. Nitrogen's pretty electronegative. Hydrogen, not so much. And so, I wanted blue. There's my hydrogen bonding when I have nitrogen-containing compounds. And then the last one's trivial. There's only one case, but what the heck? H, F, H, F. Extremely polar. This is very close to an ionic bond. Almost a full plus. But plus, minus, and bingo. There's our hydrogen bond. So, nitrogen, hydrogen, hydrogen, fluorine, hydrogen, oxygen. All right, now let's go on to the more complicated case. Well, I'm sort of back to chapter 4. Remember hydrocarbons? Always nonpolar. If you draw these, you'll see they're perfectly symmetrical, nonpolar. So the first thing I'd say is I've got nonpolar molecules. But then I've got a couple of atoms. Here's an argon and a xenon. That's just a plain old atom. Well, atoms are nonpolar. There's no polar bonds. There's no plusish side, minus side. They're sort of little spheres. So I can say nonpolar molecules and atoms. Well, how are these things going to stick together? Well, let me show you a quote-unquote simple case. This is complicated. What if I draw a tiny little hydrocarbon? Let's say that CH4. Now there it is. It just has its plain old sort of fluffy. It's got all those funny shells. It's different for a molecule, but well, they're all those orbitals, and they're the fluffy electrons. Now there's 10 electrons there, and in some sense they're particles moving around, like kindergartners running around on the playground. And their motion's just all independent and random. If you put 10 kids on the playground, is there ever a chance that all 10 kids might be at sort of one side or the other? Well, sure, if the kids are running around randomly, there's no reason why at some point that electron sort of distribution might look like that. This is just a random, temporary, let's say uneven electron distribution. Just for 1/1,000,000th of a second, all the electrons are on one side. Well, that means just temporarily, I get that. Just for 1/1000,000th of a second or something, I get that. Okay. Well, what about the molecule next to it? it had its just sort of evenly distributed cloud, but now the neighbor all of a sudden is plus. Well, what's going to happen? Plus is going to sort of draw electrons towards it, right? So all of a sudden this guy who had this nice even distribution of electrons, all of a sudden his electrons are sort of being pulled over there. Now this guy's got a minus and a plus. We'll say this is induced temporary, and we'll use the word polarity. Now, this happens, then it goes back, and everybody goes back to the way they were. But if it happens a billion times a second between billions and billions of molecules, you have this sticking, unsticking, sticking, unsticking, sticking, unsticking. And that's what's holding them together. It's not sort of as permanent as a hydrogen bond or a dipole-dipole, but it's flickering on and off, on and off, on and off so fast between so many molecules that the whole mass of them stick together. Now this is called a London dispersion force. That's our IMF. It's temporary, but it on, off, on, off, on, off, on, off between different sets of molecules, and enough such that the whole mass sticks together. Now, within this London dispersion, we can say, well, this is weaker London dispersion and stronger London dispersion. Let's look at I2 and F2. These are perfectly symmetrical, non-polar molecules. But this has stronger London dispersion. I'll come back up here. LD. Stronger London dispersion, weaker London dispersion. Well, if I look at fluorine, 2 fluorines stuck together gives me 18 electrons. 2 iodines stuck together, 106 electrons. If I've got 106 kids running around the playground versus 18 kids running around in the playground, there's a good chance that a handful of kids will run to one side of the playground and make the whole thing out of balance. 18, not as much chance. So we'll just say is like this has a greater opportunity or greater chance of uneven electron distribution. So it turns out London dispersion forces are very, very weak, the weakest of all these that we're going to look at. But I can even, within London dispersion forces, I can sort of further parse that out and say, well, everything else being equal, if something has more electrons than something else, it has a greater chance to have London dispersion forces, which means the London dispersion forces are relatively stronger. Now, page 8.14 summarizes all this stuff. The first thing we talked about that we're not really going to look at in chapter 8, but it really helps us sort of, gives us a basis to think about this and understand this, is these ionic compounds, the particles are ions. So there's ionic compounds. And those are very strong forces. You might remember from early on in the semester, we did some experiments with some ionic compounds and molecular compounds. And we said, wow, ionic compounds had high melting points, high boiling points. It's because the interparticle forces are very strong. We're going to come back to that later. So they're in their own category. We're really not going to look at this much in chapter 8 other than to just kind of say like, oh yeah, there's some particles really sticking together in a strong way. Now, we're talking about particles not so strongly sticking together. those are all polar molecules. So I could say, well, the particles, polar molecules. And these are all molecular compounds. But we've sort of divided them up into this category and this category. If they have the NH, OH, or FH, we say, well, they're just superpolar. We'll put that. A Chico state, we'll put helipolar. And polar, but not as polar. So this special case, now this is a little confusing. We said this is very strong. We're going to say weak. We're going to come back and rate these. But of the weak forces, these intermolecular forces, hydrogen bonding is actually the strongest weak force, but relative to ionic compound bonding, it's very, very weak. So we say, well, hydrogen bonding is weak. It turns out dipole-dipole is weaker. And we said, well, okay, that's just regular polar molecules. So weak, weaker, and guess what London dispersion forces are going to be? Weakest. And so I put these compounds in order. The strongest of the weak forces, less strong, weaker, weaker, weaker. So I'm going to do this. I'm going to say hydrogen bonding is the strongest intermolecular force, although it's relatively weak compared to a regular covalent bond or ionic bonding. And we'll say, okay, of these intermolecular forces, London dispersion forces are the weakest IMF. Well, let's go back and summarize here. We said these compounds or elements here, nonpolar molecules, and atoms. So what are we talking about? Well, we're talking about molecular compounds, and elements. Molecular compounds and elements that are nonpolar. And I've sort of said, gosh, of this weak London dispersion forces, these are stronger, these are weaker. And really, the trick is just, I'm going to turn this sideways. I'm going to say fewer electrons and more electrons. So within the London dispersion forces, more electrons, stronger London dispersion forces, fewer electrons, weaker London dispersion forces. Okay, so there's a whole table. I look for ionic compounds. I know molecular compounds, I start looking to see if they're polar. If they're polar, do they have NH or OH? If they don't have any of that, they're nonpolar, or they're atoms. I say, well, they're going to have London dispersion forces at least. More electrons, fewer electrons. So there's my whole spectrum. By the way, anything with electrons experiences London dispersion forces. Everything has London dispersion forces. It's just usually not as important. The way we use this is the strongest force has the most influence over the properties of the substance. So we usually start up here. Oh, is it ion? Okay, I'm going to stop there. I know it still has London dispersion. I go, well, that's it. That's the strong force. I'm going to stop there, the strongest. If I don't see that, then I check for hydrogen bonding. I know hydrogen bonding will be the dominant factor, the dominant force that influences the properties, but the stuff will still have London dispersion. If I don't see hydrogen bonding, I go down to dipole-dipole. That would be the dominant, but there would still be London dispersion. And if I get all the way down my list, I go, well, the only thing making the particles stick together are London dispersion forces, which everybody always has, but it's our last sort of force to check. Let's wrap this up on page 8.15. Okay. So it says, hey, which of these would have hydrogen bonds? Well, I see like a nitrogen and a hydrogen, hydrogen, oxygen, hydrogen, oxygen. And I might think, oh, okay, yeah, those are going to be London dispersion. But I've got to draw the Lewis structures. So I have to say, well, wait a minute. If I put that together, the only way I can reasonably assemble this thing. So sure, there's hydrogen bonding. I see that part of the molecule right here. This, nope, that's a hydrocarbon. It's nonpolar. There's no nitrogen, no oxygen, no fluorine. That one isn't going to be it. I look at this and say, oh, you know what? There's a hydrogen nitrogen. I bet that's going to have hydrogen bonding, but when I assemble the molecule, the only reasonable way I can assemble it is that. No hydrogen bonding. I go over here, same thing. I think, well, okay, the only way I can reasonably assemble this molecule is like that. There's no hydrogen stuck to there, no hydrogen covalently bonded to an oxygen, so that one's got the feature for hydrogen bonding. None of the others do. Now, problem 8.3 is really easy because I say, well, yep, nope, yes, yes, no, yes. Okay. Now, bottom of the page, here's the way we usually do this. We say, well, here's a compound. I want to recognize which IMF or which interparticle force, which glue force is most important for this compound. What has the greatest influence? Well, look at that. That's nonpolar. It's not going to have, there's no ions. There's no hydrogen bonding. There's no dipole-dipole. And the only thing I've got is London dispersion. This I could draw the Lewis structure, this ethyl alcohol, but I say, you know what? It's showing me that right there. I've got hydrogen bonding. Ethyl chloride. If it didn't have chlorine, I would see it looks nonpolar, but chlorine means there's a carbon that has carbon, hydrogen, and a chlorine sticking off of it. It's got to be polar. Now you might stop and draw these Lewis structures. In fact, you might stop and try to make these predictions and then come back and see what I said. Bromine, nonpolar. The only thing it's got going to make it stick together is London dispersion forces. Hydrogen bromide, HBr, that's got to be polar. HBr. Dipole-dipole. And there's our old chapter 3 friend. These are actually ions. So I could say ion, ion. Okay. This is similar to problem 8.4, but I made a few changes. So that's the way it works. You go down the list, check for ion, check for hydrogen bonding, check for dipole-dipole. And if as a last resort, you say, well, it's only got London dispersion forces. Now here's another thing to say here. Well, let's say this. What do they all have? They all have that. It may not be the strongest force. If they have any other force, the London dispersion just doesn't matter. But everybody always has London dispersion. Okay, so now we've got a set of forces, the names, the mechanism, the relative strength of these forces between particles. We're going to shift gears a little bit in the next set of lecture notes and say, okay, well, let's think about some physical properties, mechanisms, how they happen, and then we're going to come back and tie these with the physical properties, and that'll wrap up Chapter 8. I'll see you at the next lecture.